do a bunch of review, and then all of the stuff that is original here is joint with Jonas McCandless, who's one of my collaborators, who's over at Bonn now, but was previously at Munster. Yeah, what else do I need to say? Yeah, I think, oh, and I guess apologies for, I think, 3/4 of my oral committee, because they've heard most of this talk before, but now it's a theorem and not a, oh, we have a proof and there's a gap, so that's cool.
Wait, are you apologizing for 3 out of 4 of us, or are you apologizing for 3/4 of the material?
Well, hopefully not the latter, but I'm apologizing to the senior topology members in the. You'll forgive me, Craig. Okay, so.
Why are you ignoring the junior ones?
Well, they weren't there for my oral committee, were they, Sasha? They didn't serve on my oral committee. Okay, sorry, I'll shut up and start talking about some mathematics. So, okay, so I think that I have to talk about some background. And unfortunately, for this project that I'm going to describe, there's kind of a lot of background, and I'll do my best to be vague and hand wavy and give you a flavor for some of the ideas of what goes into this. And if you have questions, please interrupt me at any time, and I'll try to answer them as best I can. And so we're going to talk about the extremely so we're going to talk about 2 things which are kind of like sort of technical, I think. So we're going to talk a little bit about chromatic homotopy theory. And then we're going to talk a little bit about algebraic K theory. So, right. So what is, I think that not everybody in here does chromatic homotopy theory, so I sort of have an obligation to say something about what that is. So what is chromatic homotopy theory? Well, so in, I guess, in stable homotopy theory, we want to study this thing, this boldface S. This is the sphere spectrum. And one of the ways that we can sort of study this thing is to try to break down calculations of the homotopy groups of this spectrum into a bunch of different, maybe not bite-sized pieces, but pieces. In particular, maybe I should say that Serre proved in his dissertation that all of the homotopy groups bigger than 0 are finite. And so in particular, everything's torsion, which means that we can sort of study the torsion 1' at a time. And so it might be good to do something like the following. We might want to take this object, this sphere here, the sphere spectrum, and we might want to do the following. We might want to, we'll first work locally at 1'. So we're only interested in P torsion. So we're going to invert all primes that are P. And then there, we might think it's a good idea to do something like the following. We might then invert P, right? So we've inverted all the primes. And it turns out that when you do this thing, this is the Eilenberg-MacLane spectrum given by the rational numbers, which has no torsion, and everything is particularly nice. And then another thing and so this is maybe the easy part of this game, right? The rational part. And then we might think to mod out by this prime P. So we might look at the sphere mod P. We might try to understand what's going on with this thing. So just to remind everybody, you can write down the prime number P as a self map of the sphere spectrum. And this is basically like the co-kernel or the co-fiber. So you've got a map where you multiply by P. And then this thing is the homotopy co-fiber or the co-kernel, if you want to think about it in terms of algebra. And then, so we might say, okay, well, is this all we can do? It turns out that the answer is no, fortunately. Otherwise, we'd be sort of posed. There's this beautiful result due to atoms, which says that there's another self map of this spectrum. So this is atoms. And it's not null homotopic. And so what we can do is we can kind of, in the same way that we just looked at the multiplication by P map on the sphere spectrum, we could say, well, let's try to play this same game again. let's invert this thing. So we get, S mod P, V1 inverted, and then we could mod out by this V1 self. Okay, again, right? Well, this is extremely suggestive. Maybe there's going to be a self map of this thing, and then we can try to invert that self map, and then we can mod out that self map or mod out by that thing. Turns out that this exists. We call this V2, and then we can invert this. And I know some people might start to get annoyed at me in a moment here when I just write these as quotients without putting powers in front of these things, but that's fine. It's not what we want that. Okay. And we can continue this story in proceeding in this fashion, and this proceeds forever. And the fact that we can keep doing this is due to some really important work by Hawkins and Smith. So we can do this. Periodicity here. Of Hawkins and Smith. And I mean, the periodicity theorem says that, like, whenever we're at one of these quotients, when you want to think about them like this, there's a self map, and they're named appropriately according to the degree, and they do the thing that we want them to do. They're not going to be null, and so we can actually invert and take a homotopy cofiber or a quotient and proceed. And roughly speaking, the idea here is to take this hard problem, understanding this thing, and try to split it off into a bunch of different pieces where now certain there's certain periodicities which are like witnessed by these different spectra, and these form a collection of homology theories. And then the idea is to sort of stratify our information about the sphere spectrum or the stable homotopy category in accordance with all of these homology theories. And maybe what I'll just say now is I'll write down a definition, or at least a piece of notation. We're going to write Tn for first we mod out n things, and then we invert this self map, which we know exists. So we're going to write this. So this is a particular homology theory, and we're going to use this sort of notational convention that instead of first throwing away all the other primes, we're just going to invert P, and we're not going to first invert all of the other primes. Say something about why we might want to do this kind of a thing. Okay, and additionally, we're going to write down, so we want to take each of these spectra, their homology theories, and then we can sort of look at things one homology theory at a time, stratify like a spectrum according to each of these different homology theories, and then hopefully our calculations are a little bit easier, but that's of course sort of a lie. Let's see, where am I now? Okay. So I want to write down some more notation, unfortunately. So I want to write LNF. This is the finite localized, this is the Bausfield localization, where you localize at this wedge of spectra, you localize at the rationals, and then you localize the T1 up to Tn. And so this thing is what you would normally call the finite localization functor associated to Johnson-Wilson theory or Morava E theory. We can also write it down like this, but for the purposes of K theory, we're going to look at a version of this functor, which is Bausfield localization to T0 up to Tn. And roughly speaking, Bausfield localization says we're going to work in our category of spectra, and then we're going to formally invert all of the maps between spectra, which induce isomorphisms between the homology groups of this homology theory, which is a wedge of spectra applied to the map of spaces. And so we're only sort of looking at the information at each of these homology theories. So that's roughly the idea. Okay, so these are at least some construction which you can do. And I want to make sure that I've said what I need to here. Okay, so this is all pretty vague and maybe a little bit abstract, but it's perhaps worth writing down a couple of things which might be helpful. So maybe we can write down the following example. So let's say if X is a spectrum that's, say, T1 acyclic, then if we take the first localization, this first localization functor here, and we apply it to X, it turns out that this is just the same thing as taking our spectrum and inverting P. And so if you don't really care about any of this chromatic or this K-theory stuff, I'd encourage you to try to work this out as an exercise for the rest of the talk. The hint is to use that pullback square that relates to a wedge, the Bousfield localization associated to a wedge of two spectra. But okay, so this is what this thing could look like. And maybe we should also say something about what happens for other examples. So if we take a look at another example, so let's say we take, well, what do I want to do? So here's another example, is that like if you plug in anything that is like the Eilenberg-MacLane spectrum of, say, a ring or a group or something, when you apply basically, maybe I'll say this in the following way. HR has a trivial TI homology bigger than or equal to 1. So roughly speaking, each of these homology theories is supposed to correspond to some like height I or height N phenomenon that's happening in spectra. Okay, so this is the picture, and for what I want to tell you about today, these homology or these Bousfield localizations and all of these homology theories are really going to be the star of the show. All right. Any questions so far? Feel the need to like make the same remark that Craig made, I think 2 weeks ago, about we're going to write down a lot of definitions and then hopefully we're all going to maybe feel okay about it later. Okay, so if there's no questions, maybe I'll just keep going then, but I'll leave this picture up here because I think it's kind of pretty. Okay, so this is a little bit about chromatic homotopy theory, or at least we have those functors over there that we're interested in studying. Now, we need to say a little bit about what algebraic K-theory is. So that's a bit of a bear as well. Algebraic K-theory. Too quickly. So I think if you've never heard of this thing or never seen this construction before, I sort of hope that this perspective on things will maybe at least give you a sense or a flavor for what this stuff looks like. So let's maybe start with a ring R. So R, let's just say it's a commutative ring. We can consider the following category. We can consider the category, which I'll write like this. So it's going to be the omega is for finitely generated. It's going to be finitely generated projective R modules. So these are just things which you can obtain as retracts of finitely generated free modules over this commutative ring R. And then what you can do is you can take the free abelian group on isomorphism classes of this thing. So take abelian group. And then you can mod out by the following relations. So quotient relations, the form, let's get this right. This is going to be P, maybe P plus Q minus I don't know, M, if there's a short exact sequence which looks like this. So basically we're just saying that we want the sum of these two things to be equal to the middle term, and when we're projective and finally generated, that makes sense. But the point is that the result of this procedure gives you what we call the zeroth K group. The zeroth K group, K0 R, is the result of this procedure. And this thing was originally introduced, I think, in the late 50s by Grothendieck. And, you know, why might you want to introduce this kind of a thing? I mean, so one way to think about this is something like the following. You are interested maybe in classifying vector bundles over some scheme. And in this case, we have a nice affine scheme in front of us, in particular spec R. And from the correspondence between, you know, affine algebraic geometry and commutative algebra, finitely generated projective R modules are exactly vector bundles over spec R. And so these K groups are sort of giving you a way to organize how you might approach the problem of classifying vector bundles over a scheme. And there are really interesting and deep relationships between these groups for various rings, and you can also define them for algebraic varieties. And in that case, you have the sort of celebrated Grothendieck-Riemann-Roch theorem, which tells you about, gives you a relationship between the rationalizations of these groups and then the rationalizations of Chow groups, which are groups which remember they tell you something about algebraic cycles, and I'm not an algebraic geometer, so that's kind of the most I want to say about this problem. Okay, so that's a really quick description of what this K0R is. There's a lot of really interesting mathematics, like just around this example and this procedure. Like thinking about things in these terms is another way we can define topological K theory, which is ultimately a maybe more familiar thing to people in the room here. And yeah, there's a lot of beautiful mathematics here. I would totally advertise looking at Weibel's K book. But okay, in any case, these groups are sort of not going to suffice for the conversation that we want to have today. Okay, and I've already spoken for 20 minutes. That's great. Okay. So it turns out, as happens a lot of time in algebraic topology, that when we write down K sub 0, that's indicative of something. It is suggestive of the fact that this is maybe like the 0th homotopy group or the 0th homology group or cohomology group of a cohomology theory. And it turns out that there are other groups that look like this, and they have different sub-indices. So it turns out that there's kind of a few of these groups. And if I remember correctly, we only really figured out how to do these two or these three algebraically until Quillen had some wonderful ideas in the 60s. But it turns out that there's a couple of other groups which you can write down algebraically in some good cases. And Quillen showed us how to package all of this information into one object. So Quillen defined the algebraic K theory space. We'll write as KR with no subscripts. And here is sort of a ahistorical account of how you write this thing down. Okay, it's almost exactly the same procedure as what we wrote down here, except now I'm going to allow my objects to be a little bit more fancy, because that's what we need for like later on down the line in this talk. So we're going to say that here R is a connective ring spectrum, which means that there are no negative homotopy groups. And what we can do is we can consider modules over this ring spectrum, and we can also consider those which are projective and finitely generated. So we can again consider this category. And then we can take the space of isomorphism classes, or the underlying space of this category. And okay, this is a little bit different than that picture because we have a space here instead of a set. And what we're going to do in this case is we're going to note that, okay, well, I know that we can see that this thing here has the structure of a commutative monoid by just taking the sums of finitely generated projective R modules, which means that this is a space equipped with a really nice commutative multiplication. And then what we can do is we can take this multiplication, or I should say like addition, and we can group complete this commutative monoid so that this becomes a group-like commutative monoid. And so we take the group completion and it turns out the result is exactly this space that Quillen told us about. And this is the so-called, maybe I should write this down as a definition. This is the K-theory space of a connective ring spectrum. And it took a lot of work, but people sat down and checked that, you know, this space that we wrote down here gives all of these groups back to us when we check in the situations that they were defined. And why might we want to have something like this? Well, the reason we want to have something like this is that it packages all the data which we had here originally together with a bunch of different ways. It is a tool to organize all of this structure together. And now we can think about, you know, this thing has some variance in connective ring spectra as well. And so between a map of connective ring spectra, we get a map of spaces, right? And a map of spaces is strictly stronger than a bunch of natural transformations between a bunch of these abelian groups. And so this is maybe the real object that we're interested in. And this thing is quite difficult to study, as I think, I don't know if anyone's ever heard me talk about this stuff before, which I sort of feel like I've talked about ad nauseum. I think I've said that like, I don't know, 50 times or something like this. Right, so this poses a problem for us. And Sasha, can you remind me when I need to stop talking actually?
Not yet.
Okay, thank you. Very helpful. Very helpful.
Probably it's a little over half an hour.
Okay, wonderful. There should be plenty of time. Okay. So the problem is that this is really hard to calculate. And what do mathematicians do when we run into something we don't know how to calculate? The best thing we can usually do is try to relate the thing we don't know how to calculate to something that either we do know how to calculate, or at least we have a chance of calculating. And this is sort of where this TR object that I had in the name of my title is going to come in. And so what I'll say is maybe the following. So my work of a lot of great people starting I think I want to say in the 80s and going up until the present day we've introduced a bunch of comparison theories. So, and I'll write down the names for all of them. So there's this one called THH, which was defined in the 80s. There's this one called TC, which I believe was also defined in the 80s, but I don't remember the exact date of the paper. I think it was 85. And then there was this other thing, TR, and maybe someone in the audience knows, but I think this was in the 90s, but I don't quite remember. So this thing is called topological hot field homology. This thing is, I'll just say, topological cyclic homology. This thing is called topological. Can't even follow my own conventions. Restriction. And the introduction of all of these different, so maybe what I'll say is I'll say something like about what these things are. These things are invariants of ring spectra or connective ring spectra, if you like, just like algebraic K-theory. And they come equipped, they come equipped with a bunch of transformations. And they go from K-theory to THH, K-theory to TC, K-theory to TR. And a lot of the really big, important structural results about algebraic K-theory in the past 40 years or so have come from like basically working these maps and these invariants to the bone and doing a lot of calculations with them. And so these things are a very useful way to compare algebraic K-theory to something that we can calculate. This is what these things are, but I don't actually want to spend any time like really carefully defining these or describing the structure that they carry, because it is somewhat incidental to the results that Jonas and I were able to obtain. But maybe what I will say is I will give you a very strange definition for what TR is supposed to be. Okay, so I told you earlier that this K-theory construction, this thing is a functor of ring spectra, full stop, not just connective ring spectra. Not that we'll need this, but I want to define for maybe, so I don't have to write TRR, I'm going to use, so for a connective ring spectrum, we're going to define TR of A by this following weird formula. We're going to take an inverse limit indexed over n of, we're going to take a loop, and then we're going to take this funny piece of notation, which I will explain in a moment. We will take the K-theory of these truncated polynomial algebras. We will look at the map to the K-theory of A and then take the fiber of that. And so this thing here is defined, as I just verbally said, it's the fiber of the map from the K-theory of A with like a truncated polynomial, tensored with the truncated polynomial algebra down to the K-theory of A. And so this is what we're going to say TR is for today. And I think that will suffice for what we're going to talk about. And so here, how is this inverse limit formed? Well, you can always imagine taking, you can have one truncated polynomial algebra, and then you can mod out by some lower degree power, and that gives you a map from one to the other. And this is how this inverse tower is formed. But this is what we're going to call TR for today. And I should really say that this is a definition / a theorem. So, and this definition / theorem are due to a couple of people, but in particular, maybe I will write Bloch, Hesselholt, Bentley, Flick-Kroll, and then my collaborator, Jonas. So the point is that what we're treating as a definition today is really a theorem. There's another way to define this, not in terms of algebraic K-theory, and you have to prove that that's true. And this is kind of a pretty strange result if you think about it from the perspective of how I introduced these other trace invariants, because we introduced them in order to study K-theory, but then somehow one of the things that we were thinking about literally was defined using K-theory, which is just a very, very strange fact. And I would be very happy to maybe vaguely say some things about this at the end of the talk, because there's a really interesting relationship between, in particular, TR and algebraic K-theory, which I think is, in the past 5 or so years, is becoming clearer and clearer, which is kind of fantastic. But anyways, this is what our definition is for today. Okay. This is a good time to pause and see if there are any questions so far. Things are very vague, so I apologize. Yeah, David.
This is probably dumb, but is when we take when we're constructing the algebraic K-theory space, is proj omega R like taking the weak equivalences, is that a space in the sense it's a groupoid and we're just confusing groupoids with spaces, or is it something like an enriched sense?
It's well, yes to both of those questions, because yeah, we're taking something which has mapping spaces, and then we're only remembering like the equivalences which were in those mapping spaces, and so that's what gives us the groupoid, right?
Mm-hmm.
But then of course that thing is then in a space enriched. Yeah. So we're only keeping the equivalences between the different finitely generated projective modules around when we pass to this space. Yeah, that's a good question. Okay, anything else?
Liam, if you use this definition as the definition of TR,
Yes.
then the connection to the K-theory of A appears in a pretty it's not so impressive, I would say, because because you relate this build up out of K-theory of that particular ring,
Yes.
well, related to A, to the K-theory of A.
Yes, I absolutely agree. Yeah.
Which one is harder to understand?
Which one is harder to understand?
from
Well,
that perspective?
So which is harder to understand, the TR of A or the K theory of A?
No, the K-theory of that particular ring of the right.
Yes. So it is harder to understand, I would say, this thing
Mhm.
than, well,
That's harder than K.
yeah.
That's-
Well, I mean, this is the same thing as TC, right?
Right.
By DGM. So, because this is right, I mean, that's a nilpotent extension.
Mhm.
This is a pullback. Take the vertical fibers, they're the same. So, like, I mean, but again, I think Tyler's point is correct in the sense that you need to understand like TC of A, like as input, maybe to do this calculation here. And so it's kind of a weird question, because at the same, like this secretly is topological cyclic homology. And I'm using another really big theorem to identify this thing with TC. And so maybe if you were really good at TC calculations, this is like easy, but no, I don't know. It's a little hard to say. Like, you know, a priori, I would say it's easier to understand like TR of A and TC of A than it is to understand the K theory of A for sure. But since you're in this like relative situation here, you can cheat and you can identify this thing with something else.
So maybe we should think of the right hand side as if you replace K with TC
Yeah.
there, then it would simplify a lot of things.
Sure, I mean,
More or less for me.
yeah.
Because,
So
yeah.
Right, so yeah, it's hard to say, and I mean,
Now
it's
you-
also,
Now you're relating two tools to study K of A. relation to each other, basically expressing the tool called TR through the tool called TC, but it's variation of.
Yeah.
Right. But yeah. Also.
Yeah, I think another thing to say is it's just hard to do calculations in general, I think here. Even like, TC is possible to do, but it's still difficult and it takes some work. Yeah, maybe I'll move on. Sure. And sort of start talking about how the two things we've discussed so far are related to. All right. Interactions / redshift. All right, so okay, so we spent a lot of time talking about these theories over here and how K theory relates to these objects. But we also began the talk by discussing a way to sort of stratify homotopy theory or the stable homotopy theory into a bunch of different individual pieces. And the idea was, or the hope was, that somehow by looking at each of these individual pieces, we're going to get some sort of simplification happening where calculations will become easier or there will be nicer structural properties involved. And so one natural question that one could ask is, what happens when we mix these two constructions? Or not two constructions, but mix these constructions. In particular, let's just localize it one of these homology theories, and let's take the K theory of this thing. And you could ask, like, is this nicer in some sense than this? Or maybe, how does this depend on our ring spectra as opposed to this object here? So just erase this. Okay. And so there is a philosophy, or there's a general philosophy, which is due to Ausoni and Rogness, which says the following. It says that algebraic K theory shifts maybe what I'll call chromatic height by 1. So like maybe let me vaguely gesture at what this looks like with the following sort of silly little picture that I like to draw. Okay, so let's say, so we had a bunch of these homology theories, right? We had T0, T1, T2, etc. And let's say we had some like ring spectrum R over here. And we wanted to write down like a diagram of all the different heights of this ring. And maybe I'll write down a star here if the ring is like non-zero from the perspective of these homology theories. So the idea is something like this. So when we apply the K theory construction, there's going to be, so now we're going to write things like 0, 1, 2. And the point is that we're going to have something like this happening. There's going to be some transference of chromatic information up 1 degree. So in particular, let's just vaguely say something like, if your ring spectrum R is only chromatically interesting in 1 degree, meaning like when you look at all the homology theories except for one of them, and you get 0, then the K-theory of that ring will have interesting homology theory in degree n+1. This is roughly the idea of this philosophy. And so there's going to be some kind of like shifting of chromatic information when we apply this construction algebraic K-theory, which we call algebraic K-theory. Okay, and another consequence of this interaction is essentially like, if all of this was uninteresting, right? Like if we had nothing, okay, well, I don't want to write 0. Maybe I'll put like, oh, that's terrible. Maybe I'll put like 0, 0, 0, 0, 0. Like if our ring spectrum was chromatically uninteresting in a range, then the algebraic K-theory spectrum can't have any interesting chromatic phenomena happening over here, because we have this shifting procedure, which is this philosophy, which is telling us that the stuff in one height up is controlled by the stuff in one height down before we took K-theory. And so we can't have any like interesting stuff appearing here. And so in particular, we're going to get like a big fat 0 in degree n when we take algebraic K-theory. Okay. So this is roughly speaking, this Ausoni-Rognus so-called redshift philosophy. And the reason it was originally called redshift is because when we were, basically what was happening is that there was some kind of periodic phenomenon happening over in R. And then when we took K-theory or some other construction, we were seeing that now this periodic phenomenon was happening in a height in height up by 1, and the wavelength of the periodicity was wider. So this is where the redshift comes from. I feel sort of obligated to explain this whenever I talk about this stuff. Okay, so now that I've vaguely gestured at this shifting behavior, I want to tell you the theorem, which is true about this shifting behavior. Okay, and so
15 minutes.
15 minutes. Okay, lovely.
Probably 15 minutes.
Sorry.
Probably 17 minutes.
That's okay. I'll try to not take too long. So let me tell you a theorem, which is exactly confirmation of this vague thing I've just described. This is due to 4 people: Lond, Matthew, Meyer, Ms. Tama. And they tell us exactly the following: that so if R is a ring spectrum, and we know that when we take this funny localization functor of R and we get 0, another way to say this is just that for each of these homology theories up to n, R is uninteresting chromatically, then the K-theory of R is also uninteresting chromatically in a range. This is essentially confirmation of this vague idea that we've been talking about. And there are some other really lovely consequences of this theorem that maybe we'll talk about at the end if there's enough time. And so the question I want to turn to now is, to what extent does this behavior prolong to, in our case, TR? And of course, you can ask the same question about THH, about TC, and then other sort of trace theories that we might be interested in studying. Okay, so maybe what I'll do is I'll tell you our theorem. And it's the following. So for A a connective ring spectrum, which is chromatically uninteresting in the same range as before, then we know that TR is also chromatically uninteresting in the same range as before. Okay. So maybe the first thing that I want to say is that this is not a very interesting theorem when A is nice and very multiplicative. So when I've been writing ring spectrum down here, I really mean associative ring spectrum, right? The multiplication is not commutative. And what turns out is that it turns out essentially that this theorem has a really easy and really nice proof when you know your ring spectrum is like, you know, commutative enough. And you know, I think we've kind of talked about operads enough in this seminar for me to say the following. So here's a proof when R is E2. So the first fact that we need is that this transformation here from K theory to TR, this is multiplicative. Meaning that if you input something with enough multiplicative structure into both of these things, this transformation will itself be multiplicative. So like the analogy is that if you're, you know, if you have a map from the zero ring to a non-zero ring, well, you had to be the zero ring. The target had to be the zero ring because it's a module over zero, which means it has to be zero. And this is essentially the observation that you use in order to prove this in this case. So the point is that if R is E2, or maybe, you know, maybe I'll just say a commutative ring spectrum. This tells us that this map from the K theory of R, keep writing A and R to avoid this particular situation, but I have nonetheless found myself here. So this here is a map of rings. And if we knew that R was chromatically uninteresting in this range, we knew that the localization, or we knew that the K theory of R was chromatically uninteresting in this range. And Gauss field localization is also a multiplicative procedure, which means that if you have a map of rings and you take the localization, it's a map of rings. And so the source was the zero ring, so the target has to be the zero ring as well. So this basically tells us, not for free because we needed that theorem, but this tells us that TR was also chromatically uninteresting. So for example, if we took maybe, I don't know, let's take the truncated Brown-Peterson spectra with a suitable enough multiplication, or no, that's not going to be a good example for us, actually. That's a bad example in this case, sorry. That was chromatically interesting in the range where I wanted it to be chromatically interesting. But okay, in any case, we can't use this argument because we want this to hold for all associative ring spectra. And so how are we going to proceed? Well, we can try to proceed by using that funny definition for TR that we wrote down earlier. Okay, so let's write down TR as this big inverse limit. It's this scary thing. TR of A. Let's get the notation right this time. This has a bunch of loops of these relative K theory spectra. And okay, this is an inverse limit. In particular, it's a tower. And we can always write such a tower in the following fashion. We can write this as the fiber of a map between infinite products, where we do the following: we have loops, A theory, T into the I, and then this is another map to the product. Okay, and so because of the way that, because this is going to, so the point is that this object we're interested in sits in a cofiber sequence or fiber sequence with these two infinite products of spectra here. It suffices to show that, you know, one of these terms is zero because they're the same term. When we smash with, when we chromatically localize these terms. And so it suffices to work with this infinite product here. And in fact, the loop is also superfluous, and so we can ignore that as well. Okay, so we've reduced to checking that by a bunch of stuff I've said verbally, that this infinite product is going to be acyclic for a collection of homology theories. And in addition, right, I mean, we can also, because this is itself a fiber, we can reduce to showing that the infinite product over the K theories of all these truncated polynomial algebras is going to be, maybe we'll just say reduced to checking that this spectrum is Ti acyclic for, maybe I'll say TK acyclic, since I've already used the index I for K, then 1 and N. Now, the problem is that homology theories are not always, well, they're rarely well behaved with respect to infinite products. If I try to take the homology of that infinite product, I can't just take the smash product of this thing and then move the TK on into the inside. That's not how these things work. And in general, if you have a collection of spectra which are acyclic for a particular homology theory, the infinite product will not be acyclic as well. And so what we need is we need some kind of uniformity condition on this product in order to show that this thing is going to be acyclic. And the uniformity condition is coming from the fact that A is inside of each of these K theories here. And so what I'll say now is so let's remember additionally, how did we define the K theory of these things? Well, we took the space of finitely generated projective modules, and then we group completed that thing. It turns out, and here's a lovely theorem, which is due to Adriano Cordova. Oh, I can't remember where the accent goes. The theorem due to Adriano Cordova, which basically says the following, that if you take, so the construction we talked about earlier with this group completion works for any additive category, and the result, which is due to Adriano, says that if you take an infinite product and you take the K theory of these additive categories, this is actually the same thing as taking the K theory of this infinite product of additive categories, which is kind of a shocking thing. And so I will say that this is not published yet. This is work in progress, but Jonas and I have, we've at least seen Adriano's explain these arguments to us. And so because of this, what we can do is we can write down this expression, which is secretly given by the K theory of some categories of finitely generated projective modules in the following way. We can take the K theory of Raj finitely generated, the T to the I, move this infinite product inside, and then argue that the infinite product of all of these categories has to, the point is that now we can argue that this is chromatically trivial in the correct range. And we have a bit more control on this situation now because the objects in this category are just things that look like retracts of finitely generated free things. But these polynomial algebras, right, are then themselves, they themselves receive maps from A. And so the objects in here are effectively just sums of things that look like this. And the things that look like all of these truncated polynomial algebras are like, in particular, finitely generated as modules over A. And so we can sort of use the finiteness of each of these ring spectra, plus the assumption that we had on A that it was chromatically uninteresting, to show that the K theory of this has to be chromatically trivial in the right range. And I think I'll stop there because I'm over time. Thanks for listening.
Thank you very much. Questions?
Yeah.
You went a little fast, but can you say why you couldn't do that last argument just one I at a time inside of before the equivalence there?
So sorry, why couldn't we do this argument one I at a time before this equivalence here? So, okay, so if I understand the question correctly, why can't we just directly show that the infinite product of these acyclic spectra is acyclic? Right. So I don't think you can, because in general, you like, how do I want to say this? Maybe there's an argument which does this, but I don't know it. But right, the problem is that you have an infinite product of things which are acyclic, and you kind of don't have a way of getting your hands on like okay, so what would make this true here, right? Like if we knew, we would know that this would be chromatically acyclic in the correct ranges if we had something like the following. Let's smash this with TI, right? And yes, yeah, we could localize, we could move the finite spectra on the inside, and then we'd need a finite bound, right? And we can't get that, sadly. Yeah.
Do you know a counterexample of an infinite set of acyclic spectra that have non-trivial homology?
Yeah. This thing. So each of these things, like if you take, for example, the K1 localization of this thing, it's bounded above, which means that it's K1 locally, it's 0. But if you knew that this was K1 locally trivial, then like you could write down the Postnikov tower of the sphere spectrum and then write the sphere spectrum as the fiber of a self map between these terms. And that would tell you that the K1 local sphere would have to be trivial. And that's not true by calculations of Brown. But yeah, this is like this is just a funny, cute example that I really like. Yeah.
So since I can't help myself, this is also true in algebra, where if I take the product of the Z mod P to the N's, that isn't rationally trivial, even though the individual terms are trivial.
Okay, I think I believe that. Cool.
Thanks for providing sanity time. And clarity.
Other questions? I have one.
Yeah.
As per the redshift philosophy,
Yes.
the way you explained it, I would expect the answer, the I in your theorem as well as in the four author theorem would run up to n+1. Why wouldn't it be the
Yes,
case?
why wouldn't that work? So maybe what I'll say is the following. Sorry, there are a lot of examples that I'm trying to keep track of in my head, and I'm sure there's a very silly one that's glaring at me. So the question is, why wouldn't this tell us that at heights n plus one, that this would be chromatically trivial?
Right.
So let's see. So let's say that we're true.
Maybe, okay.
Yeah, so let's say that we're true. So if so let's see. So if
Maybe there is a counterexample that you can provide, but the point is that why isn't it expected to be true?
why isn't, okay, sure. Yeah, why isn't it expected to be true? Yeah, okay. So the reason for that is that the shifting behavior can be kind of funny, and sometimes there's interference and diffraction where things from height like n plus one might still impact what happens at height n plus one. So at least theoretically from the philosophy is that the behavior is supposed to shift everything up, but sometimes you can have this interference where stuff in degree n plus one is interfering and appearing in height n plus one. And I would need to sit down and think about a very concrete counterexample.
So if you look at those incarnations of K theory,
Yes.
THH, TC, TC, and TR,
Mhm.
then I know that I would expect that in C, the phenomenon will be with less diffraction or
Yeah.
what do you call it? Interaction.
Yes, your intuition is correct.
Because TC, this phenomenon, the redshift phenomenon, with C is probably related to the fact that typologically it's open. TC corresponds to open, taking the base loop space. I'm appealing to say Woodward's and Jones results about the Fock shows. Sorry, the cyclic chain complex corresponding to the base loop space.
Right.
The chain complex of the base loop space, and so in this regards, but the loop space is just omega should be by one. Is it, or is it too naive to think this way?
So I admit I don't have a direct answer to the question as you posed it, but maybe I'll say this. If, for example, you looked at, let's not look at TC, let's work even more simply. Let's think about THH. That is like, if you think about what that is a cyclic bar construction of a ring object. And there you're taking a homotopy colimit, and homology does commute with those things. And so if you just, so if you had, for example, something that was uninteresting in, say, like height n plus one, you would be able to directly conclude that the result THHA is chromatically uninteresting in height n plus one. But that's a consequence of how that thing is built. And of course, the story becomes more complicated when you think about TC and TR. But I'm sorry, I wish I could give you a better answer. I think that's the best I can do on the fly.
So what clarifies things.
Thank you. I'm glad.
Other questions? Yeah, great. Let's think. Liam was very simple. And if there are topology builds happening, there are topology builds. Thank you. Okay, thank you, Liam.
Yeah.